Hi students, welcome back. Hope you are doing good. So, are all the solutions in this universe ideal? No. There are non-ideal solutions which exist in the universe. These solutions deviate from the Raoult's law of solutions. So, in this part, we will discuss what is an ideal solution, what is a non-ideal solution, and how non-ideal solutions deviate from their ideal behavior. So, let's start our part. So, we will discuss about ideal solutions and non-ideal solutions. Ideal solution. So, in this slide, we will see about the different definitions related to the ideal solution. So, an ideal solutions are those which obey Raoult's law, and we know what is a Raoult's law, and all the solutions which obey Raoult's law are ideal solutions. So, ideal solutions obey this law, that the partial vapor pressure of any gas is equal to the vapor pressure and the mole fraction. So, partial pressure of A in a solution is equal to mole fraction of A in that solution and vapor pressure of the solution, vapor pressure of the given component A. So, real solutions show approximately ideal behavior when. So, you know that there is an ideal. Now, the solutions which are not ideal are real, right? So, just like it's an ideal gas and non-ideal gas, non-ideal gases are nothing but real gases. Here also non-ideal solutions are the real solutions. So, real solutions, they approximately show ideal behavior when the solution concentration is very low. What does that mean? The amount of solute is very low. So, if the amount of solute in a given solvent is low, the solution concentration is also low, right? Then there is a chance of real solution behaving as an ideal solution. Next important point, the solute and solvent have similarly sized molecules. So, the size of a solute should be equal to the size radius, let us call radius or diameter, size of the solvent molecule. So, in this case also real solutions may behave ideally. And the third important point, this is very important. The solute and solvent have similar type of intermolecular forces. So, you know that if there are molecules in a the solute consists of certain molecules and the solvent consists of certain molecules, and there are intermolecular forces in the solute and the solvent. So, if the solute and solvent have similar type of intermolecular forces, then the real solution approximately behave as an ideal solution. So, it is apparent from these 3 points that Raoult's law breaks down when solvent and solute intermolecular forces of attraction are much stronger or weaker than the solute solvent intermolecular forces, right? So, we have discussed how the intermolecular forces play an important role in an ideal solution or in an ideal behavior. So, Raoult's law breaks down when the solvent and solute intermolecular forces of attraction are stronger or weaker than solute solvent intermolecular forces. So, ideal solution, what is an ideal solution? So, by this time we got an idea that ideal solutions behave according to Raoult's law. They follow the Raoult's law of solutions. So, if you are having two constituents in a given solution, right? So, the total vapor pressure of the mixture will be the total pressure of the mixture is now equal to the sum of the vapor pressures of the given constituents. So, the vapor pressure of the given constituent A is nothing but its mole fraction of A multiplied by the true vapor pressure of A and mole fraction of B multiplied by the true vapor pressure of B. So P total is nothing but the vapor pressure of the mixture. So again, so P total I can write in a different way. So P total will be the, I will call it as a partial pressure so that there won't be any confusion. So the total vapor pressure of the given mixture is sum of the partial pressure of A plus sum of partial pressure of B. Even this is similar to Dalton's law, right? So the partial pressure, it can be now expressed in terms of vapor pressure when you multiply with the mole fraction of A. So the partial pressure will be now mole fraction of A times the vapor pressure of A. Similarly, the partial pressure of B will be mole fraction times the vapor pressure of B. So when you club this, you will get the total pressure, right? Total partial pressure, or I can call it as a total pressure, right? So now I can say that ideal solutions will behave or follow Raoult's law. So this is the now resultant equation for ideal gases. This is already written here. Now the important thing is, if this P total is not equal to, I mean if LHS is not equal to RHS, right? When LHS is not equal to RHS, so there are two conditions: LHS may be greater than RHS or LHS may be less than RHS. So in both cases you have a non-ideal conditions, you have a non-ideal behavior of solutions, right? So this equation works only for ideal, and we will see what are the equations which work for non-ideal solution. So this is a graph which depicts the behavior of an ideal solution, right? So you have a vapor pressure on one side and you have mole fraction of A or mole fraction of B on the other side, right? And in this graph it is just that it is just a plot between a total vapor pressure or total pressure of the given mixture and P naught of A XA, P naught of B XB. So the vapor pressure of the solution is P total, right? And if we plot a graph between mole fraction of A and vapor pressure, so this is the kind of graph you will get it. So here this is this point is nothing but the pressure, vapor pressure of A, pure A, and this is nothing but the vapor pressure of pure B, right? So this graph is important for all the examinations. Non-ideal solutions. Now we will look into non-ideal solutions. So what is a non-ideal solution? Solutions that do not obey Raoult's law are called non-ideal solutions. This fact is already known by this time. So in a non-ideal solution, solute-solvent interactions are significantly different from solute-solute and solvent-solvent interaction, and the solution is like to be a non-ideal solution. So this is fact is already known by this time, right? So intermolecular forces between components in a dissolved solution can cause deviations from the calculated vapor pressure. So because of the intermolecular forces, there might be deviations from the calculated vapor pressure, right? I told you, right? LHS might be greater than RHS, LHS might be less than RHS. What is LHS? LHS side we have the calculated vapor pressure, and because of the intermolecular forces, these two conditions might occur. And if these two conditions might occur, that is a condition of a non-ideal solution. There are two types of deviations. There are two types of deviations from Raoult's law. One is such solutions which show negative deviation from the Raoult's law, and one solution is that which show positive deviation from the Raoult's law. So the solutions in which both components have lower escaping tendency in the solution than in pure liquids. For example, you have a solution, right? In the solution you have a solute plus solvent, right? So if these components, if the components of solute, right, both solute and solvent, they have a vapor phase, right? Solute may have a vapor phase. That means this liquid molecule, the molecules of solute, I'll write it as SO, and the molecule of solvent, I'll write it as ST. So SO is a solute and ST is a solvent, right? So you will find the vapor phase of both solute and a solvent, right? You will find the vapor phase of both solute and a solvent. So what is happening here? Here the concept is escaping tendency. That is, the components present in the solution are escaping, right, to form a vapor. Remember, if the escaping tendency is very low or low, that means what happens? The vapor pressure, right? If vapor, what is vapor pressure? Vapor pressure depends on the mole fraction of or the number of particles of both solute and solvent in the given vapor phase, right? If the tendency of escaping is low, what happens? Very few components will be turning into vapor. So if very few particles are turning into vapor, what happens? The pressure is also lower. The total pressure, the total vapor pressure is also lower. So such components or such solutions in which the components are having lower escaping tendency are bound to show negative deviation from Raoult's law. So positive deviation. So this is contrary to the negative deviation. So if two liquids mix endothermically, this indicates that solute solvent interactions are weaker than interactions among the molecules in the pure liquids. So if the solute solvent interaction is weaker, that means they have higher tendency to escape, higher escaping tendency. So if they have higher escaping tendency, they will be having higher vapor pressure. So vapor pressure will be higher. So such solutions are said to be having a positive deviation from Raoult's law. So for such solutions, more energy is required to expand the liquid than which is released when liquids are mixed. This is apparent. So the molecules in the solutions have higher tendency to escape than is expected. Let's consider a solute and a solvent. So when you have a mixture of ethyl alcohol and N-heptane, so this mixture of ethyl alcohol and N-heptane, they have higher escaping tendency because of weaker solute and solvent interactions, and this increases the vapor pressure of the given solution, and they are bound to show a positive deviation from Raoult's law. This slide gives you a clear picture in terms of a graphical manner. So we know the graphical representation of an ideal solution. So the vapor pressure of the solution depends on the partial pressure of A and partial pressure of B, right? We have discussed this. And now when you are having a positive deviation, I told you, right, when you are having positive deviation, the vapor pressure of the solution is increasing, right? So this was the normal vapor pressure of the solution, this was the normal pressure of the solution, right? And because of higher escaping tendency, the vapor pressure of the solution is increased. So this results in this kind of graph, right? Why? Because the partial pressure of A and partial pressure of B both are increasing. Also vapor pressure of the solution is increasing. Now, when you're having a negative deviation, that means they have strong intermolecular forces or lower escaping tendency. Vapor pressure of the solution is decreasing, right? And because of this, the partial pressures of A and B are also decreasing, and finally the vapor pressure of the solution is less compared to the true vapor pressure, right? This is the true vapor pressure. This is the vapor pressure of the solution which shows negative deviation.
So students, we have discussed important concepts related to ideal behavior and non-ideal behavior of solutions. We have seen how non-ideal solutions behave differently from ideal solutions. We have seen the positive deviation, we have seen the negative deviation of a given solutions.